Welcome back to the Sci-Cast, the show where we discuss all things science. I'm joined by Harry, Zaynah, and the mysterious Dr. X. Today, we discuss relativity in satellites, the triple point of water, neutron stars, and the ultimate goal of everything, apparently. I'm Max, and this is the Sci-Cast. Now, before we begin, we have a surprise. Zaynah has a camera. And here she is. Finally, how does it feel to have a camera?
I have no words.
No words. Oh,
Life
brilliant.
changing.
And Dr. X, I mean, if you're not going to reveal your name, goodness knows if you're ever going to show your face. So, I like the mystery, though. I like the mystery. All right, awesome. So we've got 3 out of 4 of us with the cameras, which I like. I want to start first by congratulating all the men and women who have worked tirelessly on the Mars rover Perseverance. It's another extraordinary feat in the world of space exploration. And who knows, maybe David Bowie's question will finally be answered. The reason we aren't discussing this today is that by the time this episode reaches you, it will have been well over 2 weeks since it landed. And who knows what it will have discovered by then. Maybe there was, or indeed is, life on Mars. Right, I'll shut up. Dr. X, tell us about, in your words, I must stress in your words, the ultimate goal of everything.
The ultimate goal of everything. Okay, well, let's start off with your goals. What are your goals? What's your ultimate goal? It's a big question, I know, but just come up with an answer on the spot.
That's a big
Start
question.
with Maximilian.
That's a big question. To be happy.
To be happy. That's a brilliant goal. Harry G.
Probably to find a job I enjoy that also provides enough free time to do all my hobbies like reading and playing the guitar.
Nice, sounds good. And the fabulous Zaynah.
Well, I was going to say to get a house, but that sounds a bit superficial now.
That's fine. Okay, right. So those are our goals. Now I'm gonna move on to the experiment. Well, it's not really an experiment. It's more of an activity I'm gonna get you to do. What are your containers? What are your objects? What did you bring today?
Oh, I am Lego. I'm
Lego.
finding my love for Lego.
Nothing.
I have a pencil case.
I have a pot of pencils and pens.
Ooh, I see. Okay. Well, now I want you to pour them all out.
All right. So you want to pour us out, do you?
Yes.
All right.
At the same time?
Yeah. Nice, lovely. So, how would you guys describe that? Let's start with Harry. Describe what you see.
Painful.
Painful. Why painful?
So I now have to clear it up.
That's true. Yeah, it's just a mess right now. Okay, what about you, Zaynah?
What I can see, or when I was doing it.
Describe what you can see.
A mess.
A mess. Nice and simple. And Max?
Yeah, it was nice to pull it out, but now I realise I've got to pick it up again.
Yeah,
I'm not
exactly. What you're gonna have to do, you're gonna have to pick it all back up and put it back into this container, and it's just so much easier for it to be out there. If you're trying to move everything back into this one container, you've got only so many different ways you can arrange things, right? But if you have them out on the table, there's so many more different configurations. Like you could put your hands on them and move them around a bit if you want to, and it feels more likely that you have all of this stuff outside of the container at some point than it is that you're going to have them inside of the container. There's so many more possibilities outside. But moving on then, while you guys all pick that back up and put it back in the containers, which is why I don't have it.
You want us to pick this all up?
Yeah, pick it all up, put it back in.
Oh my word. About the ethics of this experiment.
How is that fair?
While you're doing that, I'm gonna make a small disclaimer. I am not a physicist, but I do want to talk a little bit about physics. And I'm gonna start with rule number 1 of physics: energy is always conserved. So what does that mean? Well, in very simple terms, energy is essentially the ability to do stuff, and we can kind of measure it. So if we imagined Lego, for example, was energy. So you had 1,000 Lego bricks, and each Lego brick was a unit of energy. Then you could build a Lego set with all those 1,000 Lego bricks and have loads of energy in one place. Or you could take some of those Lego bricks and you can move them somewhere else, and that would be like a transfer of energy, but you still got 1,000 Lego bricks in total. They're just distributed into different places. So that's effectively what the conservation of energy means. Okay, so why did I tell you that? No, seriously, I have no idea. Why did I tell you that? Let's just move on. Imagine you were in a small room with a large amount of people. How would you feel?
Threatened?
Who's gonna answer first? Sorry.
Claustrophobic.
Yeah.
Okay. What if it was a music concert? Loads of people crowded together, but you're enjoying music together. You're kind of dancing and stuff, right? How does that feel?
Energized.
Yeah, energized. I love it.
I've never been, so I don't know. Sweaty, maybe.
Sweaty. I love that. And Harry?
I was going to say energetic, so basically the same as Zaynah.
Energetic. I love that. Well, that's exactly the word that I wanted you guys to use. But that energy is brilliant and everything. But surely, eventually, things get a little bit too sweaty, and when the concert is over, you do kind of want to go and relax again, have a nice rest, all that stuff, right?
Definitely, yeah.
Nice. Okay. So, why would I bring that up? Well, this is sort of effectively what any particle ever wants to do. It's when it's in a high energy state, when you've got loads of particles in around the same place, it's in a high energy state. And that's great. It can do loads of stuff, it can do loads of work, but eventually it's going to want to get to a more stable state where it's just got less energy, where it's got more space. And when particles do that, it's usually called diffusion, and you're moving from a high concentration to a low concentration. So that is the goal of any particle, and to sort of bring everything together, like what we were doing in the beginning, you can kind of see that there's a higher likelihood of finding all these particles spread out than find them in a specific like small area. Just like there was a higher likelihood of having your stuff spread out all over the table and even on the floor than having them in the specific containers that you set for them. And what that effectively means is over time, everything progresses towards that messier state. Messy being the words that you guys used at the beginning. And so it feels like the universe is always heading towards this state of complete disorder. And that is often called entropy and an arrow of entropic time. And I just thought that was really interesting. I also thought it was a great excuse for never having to clean up my room, because why bother? Everything's inevitably going to end up messier anyway.
Yeah, I mean, look at the state. I mean, I'm not going to show you the state of my room because it's horrific, but yeah, no, I can totally get that.
So if everything's purpose in life is to, well, not quite purpose, but aim is to spread out, to diffuse,
Yeah.
then wouldn't that make gravity everything's biggest enemy?
That's a really interesting question. You're gonna have to ask a physicist. What I will say is, when I say like the aim of everything, obviously it's not really an aim. It's just what's gonna end up happening because of probability, really. But as for gravity, that's a whole different ball game for me to look into.
We now transition from the world of pouring Lego and energy, and indeed entropy, to the world of orbiting satellites. And now understanding relativity lets you use your phone. Now, you may have heard of the theory of relativity, and if you had, that's good. If you haven't, I'll give a brief explanation shortly. It's arguably one of the most famous theories in physics, and produced by arguably one of the most famous scientists ever, Albert Einstein. Now, relativity is split into two parts, and I'll go over each: special relativity and general relativity. Special relativity basically says the faster you travel, the more time slows down relative to something that isn't traveling that fast. So, for instance, if you have two twins at the same age, of course, on Earth, and one of them stays on Earth and the other gets on a rocket and travels really fast, near the speed of light, towards a nearby star for a couple of years, and then comes back, when the rocket twin returns, the twin on Earth is actually older than the twin because time has slowed down for the twin on the rocket. Now, this example is actually more complex if you delve deep, but hopefully it gives a rough idea of relativity. And then there's general relativity, which basically says the closer you are to the center of a gravitational field, the more time slows down. Now, you might have seen the film Interstellar. If you haven't, if you're interested into this sort of stuff, definitely recommend it. In the movie, there's a section where the group who are exploring space go to a very large planet, and half of them go down to the surface of the planet, while the other half stay in orbit, so further away from the center of the planet. And when the people on the planet who were on the surface of the planet return, after what felt for them like 1 or 2 hours, was actually around 30 years for the people in orbit around the planet, because time has slowed down for the people near the surface, whereas it's sped up relative to the people on the surface for the people in orbit. It is very crazy. And the reason it doesn't significantly affect us is because in the real world, its effects are near almost negligible. Only on the extremely big or the extremely small do they have some kind of effect. Except for one thing, which is satellites, as I mentioned. Now, the first satellite was launched in 1957, which is shortly after Einstein died in 55. And nowadays, there are just under 3,000 operational satellites in orbit. And satellites travel fast, around 14,000 kilometers an hour, and they're far from Earth relative to us. They experience 4 times less gravity than we or objects do on the surface of the planet. So, as a result, applying the rules of relativity, it turns out that satellite clocks, which are very accurate, by the way, they have to be accurate, they tick at 38 microseconds faster than the clocks on the ground. Now, you're probably inclined to say, Max, that's still negligible, and you'd be right to a certain extent, but in the world of computing, that's quite a lot. And although it seems small, it would result over time in pretty large navigational errors, because obviously satellites use, GPS uses satellites to help us navigate. And if it wasn't fixed, the entire GPS network around the world would fail within 2 minutes of operation. So there is a simple fix to this, which they do, where they just adjust the satellite clocks to tick ever so slightly slower than the clocks on the Earth to account for this and to synchronize all the clocks. So there you go. There is actually a use for relativity.
I mean, it's kind of like time travel, isn't it?
It's,
Like, especially with the Interstellar example. It's like sort of traveling into the future. For you, it's only been like, I don't know, maybe a couple of minutes, a couple of days, but then for everybody else, it's been like years and years.
yeah, it's weird. I mean, bear in mind, my examples are quite simplified, and I think there are actually more complex things to consider. If you want to read about it, but yeah, it is really weird. And black holes, which are gargantuan, I'm sure Harry will know about this, but they are gargantuan bits with such a strong gravitational field that time slows down immensely near the center, and it's still under research.
Wait, so you know how the Earth's like center of gravity, like the Earth is the center of gravity, it's a huge one that we're all affected by. Does that mean that like my head could be going through time at a slightly different rate than my feet?
Yes, I suppose it could. I suppose. I mean, it would be negligible, extraordinarily negligible, possibly, yeah. And now to the wonderful but wet world of water. Zaynah, tell us about the triple points of water.
Great. So I don't know if any of you have seen this in the news, but recently in some areas of the world, it's been so cold that people have videoed themselves throwing boiling water into freezing air just to prove how cold it is. And it actually looks really cool. So this got me thinking about some of the amazing properties of water. Dr. X, what do we call H2O in its solid state?
Ice.
Lovely.
Ice.
Harry, in its liquid state?
Water.
Well done. And Max, in its gaseous state?
Steam?
Yep, or water vapor. So water can actually exist as these 3 states at the same time. And this is called the triple point. So on a graph, the triple point of a substance looks a little something like this image, and it does look a bit complicated, but in essence, this is the point where the solid, liquid, and gas transition curves meet, and where all of the phases can coexist in thermodynamic equilibrium. Okay, so for this specific point to take place in water, the temperature must be 0.01 degrees C and 0.006 atmospheres. Now, at this point, it's possible to change all of the substances to ice, water, or vapor by making infinitely small changes in pressure and temperature. And of course, this point is unique to all substances. So if we finish off looking at cyclohexane, I just love this video because it's what some students stumbled across while they were in class. And you can see that it basically just looks a bit confused, and it does the most unexpected things when these three phases occur at the same time. So as you can see, just a really tiny change in pressure or temperature can cause it to flick between one state and the other. And what they're doing is vacuuming out the headspace of the flask, which is the gas just above the liquid. And by removing that, we're changing what we call the equilibrium. Now, the system wants to restore this equilibrium, and that means you get more and more cyclohexane molecules evaporating out of the solution, but it takes energy to do this. So the remaining cyclohexane drops in temperature and freezes. And basically, it's just a whole cycle of solid to liquid to boiling to gas, back to solid, over and over again. And this is the triple point of the substance.
Okay, this is a weird question, but what are your favorite states of matter?
You mean like solid, liquid, or gas?
Yeah,
I would say gas.
gas. Right.
What about plasma? Does that count?
Yeah, surely.
I'll go plasma.
Gotta
Yeah.
love some Bose-Einstein condensate.
Of course, of course. Could you explain that to us?
No.
Ooh. Wait, what about
I
plasma?
used-
Can you explain plasma?
The plasma.
Pardon?
Sorry, what did you say?
Could you explain what plasma is? Very briefly, very briefly.
I don't know. I just said it because I just heard of it. Isn't it like it's above gaseous state, right? It's like
It's
fire.
I think it's like more gaseous than gas. I don't quote me, but like
I feel like
It's
Harry
when-
knows.
It's when you heat a gas so much that because of the speed and force of the gaseous molecules flying around, they actually become ionized because as they hit each other with such an impact.
cool.
Pretty sure like electrons are transferred, so they end up becoming, it's basically ionized gas.
Right, yeah.
Wait, so Zaynah, is there like a point where you can have all 5 states, like a quintuple point or something?
Whoa. Wait, so water can be in plasma? Wait, no, I need that explained again.
Question, can it?
I don't know.
There's also a 6th state of matter.
I didn't even know this. So I think probably with great difficulty, because you need such a specific condition just for the 3 states, the 3 states that we're all used to and can see in real life. So it's worth researching.
Definitely.
According to Google, water cannot be in a plasma state because it's too energetic a state to coexist with water.
Oh,
So
there
there's
we
actually
go.
no plasma in the liquid water itself.
Yeah.
And it definitely can't be with the 5th or 6th state. 6s are like, I think it's something like fermionic condensate. And the 5th and 6th state are so dependent on the situation that I highly doubt you can have them at the same time as something else.
And finally, Harry discusses the scintillating nature of neutron stars.
Yeah, so Neutron stars, one of two possible outcomes from the death of a supergiant star, the other being black holes, and both are equally as extreme. As you probably know, stars burn from constant fusion reactions at its core, releasing massive amounts of nuclear energy. This is because the gravity is so strong that it squeezes materials together and nuclei fuse, the general reaction being hydrogen fusing to make helium. Eventually, the supergiant star will start to expand, fusing heavier and heavier elements from carbon to neon to oxygen, etc. This keeps going until it reaches a certain element, and does anyone know what that element is?
Is it
Is
iron?
it? Ah,
Yep, it is iron. And as iron has no energy to give, the fusion reactions stop taking place. And as the energy from the fusion reactions is what counteracts the gravity, which causes the star to collapse, well, then the star ends up collapsing into its iron core. The pressure of this is so big that electrons and protons fuse into neutrons and neutrinos. The neutrinos escape easily, but the neutrons compact into an atomic nucleus, occupying the smallest space possible. This causes an implosion, also known as a supernova explosion, and the only thing that is left are the neutrons, making it a neutron star. And to put this into perspective, this is like compressing something over twice the mass of the sun into a city.
What?
Yeah, and as you
That's
can imagine, the density of this is massive.
That's insane, yeah.
The Earth's density is roughly 5,000 kilograms per meter cubed, and a neutron star density is 1 times 10 to the power of 17, which is 100 quadrillion kilograms per meter cubed.
That's heavy.
Yeah, so a teaspoon of neutron star will weigh 1 billion tons.
Yeah, wow. That's just hard to comprehend how dense that is.
so it'd be too difficult for me to eat it because I couldn't lift the spoon.
Yeah.
Yeah.
Also, the gravity from it will, I'm pretty sure, actually will shred you, even just
Oh,
being
nice.
within like
I'd-
8 inches of it.
I'd become the food.
Yeah. And a fun little fact is that a neutron star's surface burns at 1 million degrees Celsius, which is insane because the sun's surface is 5,000 degrees, well, 5,500 degrees. So yeah, it's way more hot. And after a neutron star has formed, it spins incredibly quickly, up to 60 times per second. And if it's born in a binary system, it can spin up to 600 times per second. And the Kurzgesagt in a nutshell channel described it as a celestial ballerina, which I thought was pretty accurate, actually.
Definitely, yeah.
But anyway, the spinning creates pulses due to its magnetic field, creating radio waves, and this type of neutron star is called a pulsar. In fact, the magnetic fields are so strong that it is a quadrillion times stronger than Earth at 1 times 10 to the power of 11 Tesla. And these are called magnetars until the spinning slows down. And sometimes you can get two neutron stars orbiting each other, and they will slowly gravitate towards each other until they collide, creating a kilonova. Now, this sounds absolutely disastrous, but in fact, it's incredibly useful, as the matter released from the kilonova are heavy materials, not from fusion, but rather heavy neutron-rich matter falling apart and reassembling. The reason as to why this is great is because this is one way any material heavier than iron can be formed, which is most of the elements we know about. So after the kilonova, the two neutron stars collapse and their combined density creates a black hole. And theoretically, pretty much all of our technology are thanks to previous kilonovas, as any rare earth metal will have been made from it.
That's all from us today. Thank you once again to Harry, Zaynah, and the mysterious Dr. X. Be sure to like, subscribe, share, and check out our other videos. Goodbye.